Hi everyone, I'm going to give a brief overview of our work on developing RADICAL, which is a deep learning framework for precise inference of network dynamics from Cosyne imaging. Two-photon Cosyne imaging is a powerful tool to monitor hundreds to thousands of neurons in the brain, usually with cell types identified, and provide great opportunities to understand network-level computations. However, there are challenges with Cosyne signals, as they are a lossy, low-pass, delayed transformation of the underlying spiking activity, and the transformation is also nonlinear. The best algorithm to reconstruct the spikes might give reasonable estimates on coarse timescales, but on fine timescales that are important for linking to behavior, the estimates are poor. Due to these challenges, it is hard to infer the neuron's activity and the underlying network states from Cosyne signals. The way we improve this is to utilize the power of neural population, because we know the neuron's activities are not independent, but rather are coordinated across the population. Here we apply the dynamical system framework to Cosyne signals, which attempts to uncover the coordinated patterns of activity across population and learn how they change over time. To do so, we developed RADICAL, recurrent autoencoder for discovering imaged Cosyne latents. We built RADICAL on alphas, which is the state-of-the-art method to model neurodynamics from spiking activity. We first modified the cost function of alphas to adapt to the statistics of the deconvolved Cosyne events. Next, we developed a cool way of integrating the sampling times of two-photon to get higher temporal resolution. Please come to my poster and I will introduce the details on how we achieve subframe resolution using a novel neural network training strategy. To test RADICAL, we first use simulation. We have a synthetic system to generate the deconvolved Cosyne events. Our goal is to infer the latent states of the hidden dynamic system. Here we compare RADICAL to smoothing and auto alphas, which is a brand new framework to perform automatic hyperparameter tuning for alphas. We can run the hidden dynamical system at different speeds to assess how good the method captures features at different frequencies. When it's 7 Hz, both auto alphas and RADICAL infer latents pretty well, much better than smoothing. When it's 15 Hz, RADICAL performs much better than auto alphas. Here is a summary plot. RADICAL start outperforming auto alphas when the frequency gets higher. Next, we test RADICAL on two-photon activity from mice performing a water grab task. The sequence of the task is hold, lift, and grab the water. Here are the hand trajectories going from the pot rest to water, color-coded by conditions. We tested RADICAL on two different brain areas, M1 and S1, and also on two different mice. First, we show that at the trial average level, RADICAL captures the key features in the empirical PSDH. Next, we show that RADICAL also denotes single trial activity and reveals structures that you don't see with smoothing. We then computed the correlation coefficient R between the inferred single trial rates and the empirical PSDH to assess how good these single trials capture the empirical PSDH. And we can see across brain areas, RADICAL is doing a better job than auto alphas. Next, we visualize the neural trajectories by projecting the population activity using PCA. As we can see, across brain areas, RADICAL reveals clear structure on single trials. Next, we quantify how good RADICAL infers network states by decoding hand kinematics from the inferred firing rates. So here is the true hand positions. And here are the decoded hand positions. Comparing smoothing and auto alphas, we can see RADICAL gives better prediction. We then quantify the decoding performance using R squared. RADICAL shows the highest R squared across position and velocity, and across M1 and S1. Conclusions. First, we developed the RADICAL, which builds on alphas to precisely estimate network states from noisy Cosyne events. Second, RADICAL outperforms auto alphas and smoothing in capturing higher frequency features in simulation. Third, RADICAL precisely estimates network states and outperforms auto alphas and smoothing in decoding kinematics in real data. Thank you for watching. I look forward to seeing you at Cosyne.